So far we have been assuming that if the MOSFET is in pure saturation, and if it is an ideal MOSFET, then any fluctuation in the drain to source voltage does not create a current, there is no current. But if there is channel length modulation, okay. So ideally the MOSFET, so far we have been looking at MOSFETs that look like this, but if there is channel length modulation, the MOSFET characteristics would look like that, and technically speaking a small fluctuation in VDS now will cause a fluctuation in IDS here, okay. And the way we want to take into account this channel length modulation effect is we will consider two circuits in parallel. From now on, whenever we say channel length modulation is important, we will say that there is a MOSFET that is where there is no channel length modulation and a finite output resistance in parallel to this MOSFET, which takes into account this channel length modulation term. This RO is essentially the slope, it is dou VDS by dou IDS when the MOSFET is in saturation. Okay, so that is the output impedance that we are going to add on to the MOSFET in this parallel fashion. So now when we say that there is a VDS fluctuation, there is going to be no current in this MOSFET, but there will be a current here, and this current is basically the channel length current of the non-ideal MOSFET. So the non-ideal MOSFET is represented as a parallel combination of an ideal and a ideal MOSFET and a resistor in parallel, and that resistor corresponds to the channel length modulation. Okay. So now this is the physics, this is the connection to the device physics, because you all understand what channel length modulation is. But now let us see what impact it has on circuits. So now let us redo the understanding of the gain. Okay, what is the small signal gain now? Now we will consider non-ideal MOSFET. Okay, so you see there is now a channel length modulation resistor. So we have a non-ideal MOSFET. So what is the gain? So we solve Kirchhoff's law here, current law. So the current coming down this node is the current through this and the current through this. Okay, so let us call that I1, I2, I3. So I1 is nothing but 0 minus V out by RL. I2 is 0 because this is an ideal MOSFET. In parallel to this ideal MOSFET is the channel length modulation parameter, and therefore I3 is V out by RO, and these two together give you the non-ideal MOSFET. Okay. So therefore we have I1 is equal to I2 plus I3, and therefore you have this equation which is, I am sorry, your so let us now okay. So let us now consider using the non-ideal MOSFET in your amplifier. It is the exact same circuit as we discussed before, but the only difference is we now have a non-ideal MOSFET, okay, which is essentially the combination of this ideal MOSFET and this channel length modulation resistor. Now what impact does channel length modulation have on the voltage gain of your circuit? Okay, so once again we will solve Kirchhoff's law at this point. We will call that current I1, the current through the MOSFET is I2, this is the ideal MOSFET, and this will be the channel length modulation parameter, which in combination with I2 gives you the non-ideality effect. So now what is I1? So we need I1 equal to I2 plus I3. What is I1? I1 is 0 minus V out by RL. What is I2? I2 is going to have, there is going to be no impact of V out on I2 because this MOSFET is now ideal. okay, and all the channel length effect has been channel length modulation effect has been taken into account in RO. So, this current due to V out is going to be 0, but there is a gate to source fluctuation which is Vn. So, I2 is going to be Gm times Vn, and I3, which is a channel length modulation effect, is going to be V out by RO. So, these two together represent the non-ideal MOSFET, which is ideal MOSFET with no channel length modulation, and this is the channel length modulation effect. Okay. So, this will result in a gain being minus Gm RL parallel with RO. So, earlier with no channel length modulation, if you recollect, the gain was simply minus Gm RL, but now the channel length modulation resistance will appear in parallel with RL. Okay. So, it reduces the gain a little, channel length modulation reduces the gain a little. So, now what is the output impedance of the non-ideal MOSFET? So, we will do our same experiment, we will apply a test voltage and we will measure the test current that is going in, and we will forget about any input voltages etc., we will ground all those nodes. So, what is the current through this branch now, through these two devices? This unit will not take any current because a fluctuation in Vt does not matter, but there will be a current due to channel length modulation effect, and therefore, this node will carry a current of Vt by Ro. And what about the current through that resistor? It is going to be Vt minus 0 by RL. So, therefore, the total current is going to be Vt by RL plus Vt by Ro, which is basically saying that my Z output is Vt by It is 1 by RL plus 1 by Ro, which is RL parallel with Ro. So, that is the output impedance. So, again you can see the pattern here, you can see the output impedance into the effective transconductance is the gain, okay, but that is how you calculate the output impedance. So, you are now familiar with using small signal analysis to calculate different circuit aspects. So, now let us look at the next question. Okay. So, we know what the gain of the circuit is. So, how do I increase gain? Okay. I want to make the gain higher. How do I increase gain? Okay. The first since this is going to be the gain, how do we increase it? The first could be try and get rid of channel length modulation, but that is not really a very practical solution, right. You can't get rid of channel length modulation. So, Ro is not going to change, that is there to stay. What about changing Gm? Now, that is possible because what is Gm? We said that Gm is mu Cox W over L into Vgs minus Vt. So, how do I change Gm? I can increase the mobility, but that is not very practical because the mobility is defined by a semiconductor and it is the foundry that decides the kind and the quality of semiconductor they use. Can I increase Cox? It is possible if you ask the foundry to use a higher epsilon ox and a lower T ox, okay, but that is again in the hands of the foundry or the person who makes the devices for you. Can we increase the aspect ratio? Most definitely, because that is under your control. You do the layout, you do the design, you can decide the channel width and the channel length as long as they fall under the design rules of the foundry, and therefore, this is something you could definitely use to improve Gm. Okay. What about the gate to source voltage? Yes, we can increase it, but only to a certain limit, right. We cannot make it greater than the maximum supply voltage used for the technology. And what about Vt? Vt we cannot play around with Vt too much because it is the foundry that decides the dopant concentration, the flat band voltage, etc., etc. So, this is not something that we can play around with. So, these are not things that we can play around with, but the aspect ratio and VGS is definitely something we can adjust. So, let us say we have done our best and picked the best possible GM, we have played around with this. We can't do anything with the channel length modulation. What about the load resistor? Can we increase the load resistor? Technically yes, you can increase the load resistance to give you high gain, but there is a certain limit, right. You cannot make the load impedance very large. See, for example, let us say I keep the circuit, I say I am going to continue increasing the load resistance, and I am simply going to have an open circuit there. Okay. So, this is going to be my amplifier circuit. So, I have my V in here, I have my V out there. Does it mean that I am going to have very high gain? Can I use this equation and say that RL is infinite, therefore infinite in let us say RO limits everything, infinite in parallel with RO is basically RO, and therefore my GM is very large. Can we say that? The answer is no, because clearly you can see that the V out here is not going to remain V out, it is going to go down all the way till 0, or it is going to become very small, okay, and there is going to be no current in the circuit. Okay. So, there are, it does not seem like a solution that that is going to be readily that is going to solve your problem. So, what is the catch here? So, what is it that you observed? So, as you increase RL, you will find that the DC value of the output node starts dropping, okay, because if I want to set a constant current, let us say the current is kept constant and we start increasing RL, okay, the voltage drop here becomes IRL, the voltage drop starts increasing, and therefore V out, the DC voltage, the V out starts dropping. And if it drops too much, if you keep increasing RL and if the voltage drops too much, then this transistor will move out of saturation and it will enter linear region of operation. Okay, it will start operating in a linear mode. And what is the problem in linear operation? The problem in linear operation when you use it as an amplifier circuit is that any fluctuation in V out will now start pushing a lot of current through this device, because now this device has got a resistance of RO linear, okay, which is very small. It is much smaller than RO, and because if you recollect your output characteristics of the MOSFET, this is the linear resistance, that is RO as you have shown it here, because that is RO in saturation and this is RO in linear, and these two appearing in parallel will simply be dominated by RO linear, and the effort of all your large RL in order to achieve this will essentially be limited, because this parallel combination is also going to be determined by linear. So, you cannot increase RL forever, okay. So, that is the message of the story. Plus there are many other factors such as your swing of your output goes down, etc., but nevertheless you cannot increase RL forever. You can increase it a little but not forever, but there is a limit to it. This you can't do anything, and this you can definitely increase, but you can increase it by improving your aspect ratio. But now let us say I am not happy with the situation and I want to definitely improve RL. What options do I have? So, in our attempt to try and increase RL, let us try to have a circuit which has two n-MOSFETs. Okay, we have an n-MOSFET driver which is biased in saturation, and an n-MOSFET load which is biased in saturation. Okay. And in order to make sure that these two are biased in saturation, you can do a DC analysis, which I will leave as a homework problem, wherein you just equate the currents in these two devices. So, you see that this is the current in one saturation device and this is the current in the other saturated MOSFET, and by equating these two currents we know we obtain a relation for V out, and all you have to do is ensure that V out is greater than Vg2 minus Vt, and that VDD is greater than or equal to Vg1 minus V out minus Vt for both these MOSFETs to be in saturation. So, we have a situation where the DC conditions are set such that the driver MOSFET is in saturation, the load MOSFET is in saturation, and both are n-MOS devices, both of them are n-MOS devices. And since it is a driver, we are going to replace VG2 with a small signal input from the sensor, and VG1 is a DC voltage which is used to just bias, keep things under right bias conditions. So, there is no AC signal there, okay, and therefore, this will end up becoming AC ground when we do the AC analysis. So, let us take this case, and why have we chosen an n-MOS device? The hope is that the n-MOS device can be engineered through aspect ratio, through applying VG1 in a suitable manner, etc., to make sure that V out is always kept finite and it is always kept keeping MOSFET, the driver MOSFET in saturation, unlike the case of using a resistor. So, that is the hope, and we hope that this is going to give us large gain, because now we can use many more parameters to tune the resistance of the MOSFET, but let us see whether that works out. So, the small signal analysis is like this. So, you have, that was the load MOSFET, that is the load n-MOS transistor which is sitting in saturation. This is the channel length modulation resistor of that load, and this is like an ideal n-MOS transistor, and in combination they give you the non-ideality effect. And the gate is grounded because this was a DC bias signal that we had applied. So, that is grounded, it is AC ground, and now we have a small signal ACV in into the driver of the circuit, the driver MOSFET, which is also an n-MOS which is in saturation. So, now again writing Kirchhoff's law here, what are the currents in these 4 nodes? Okay. So, the current through this transistor here, this current is not influenced by V out, because this is representing the ideal MOS, and therefore, this current is simply GM of the driver into V in, that is this. What is the current here? The current here is V out by RO, okay. So, that current is V out divided by RDO. What is the current through this channel length modulation parameter? So, that current is minus V out by RLO, and this current here, is there a current here firstly? So, this current here is not going to be present because of a VDS difference, because it is in saturation, but let us look at the VGS. If there is a VGS fluctuation, there will be a current of GML into VGS, and what is VGS? It is VG minus VS. The VG is grounded, but what about the VS? The VS is basically V out. So, therefore, there is a current, and that current is minus GML into V out, and this is the key to, this forms the bottleneck of using the circuit in order to address gain. Okay. So, let us use Kirchhoff's law. So, the total current through this branch here is this, and the total current through that node there is that, and by equating these two you end up with a gain that looks like this. Okay. So, the gain has got GMD, which is the driver, multiplied by a parallel combination of these 3 resistors. You have RLO, which is high because it is the output impedance. It is the output impedance of the MOSFET in saturation, it is very large, in parallel with RDO, which is also the output impedance of the driver MOSFET in saturation, that is large, but the parallel combination with GML is going to reduce this entire term. It is going to make this entire term small, because GML, 1 by GML is a very small number. Why is that? 1 by GML is nothing but 1 by mu Cox W over L into Vg2 minus Vt. Okay. And this, if you think of it numerically, it has got the same numerical value as the output resistance of the MOSFET in linear mode when we looked at the analysis of a switch, and we already know that this is going to be designed to keep it very low. Okay. So, 1 by GML is very small, this is a small term, and therefore, this entire parallel combination is going to become small, and therefore, the gain is going to become small. If only if this GML, if this term were not present, the gain would be very large. And what is that GML due to? It is due to the gate to source voltage of this MOSFET, of this load fluctuating, because it was an n-MOSFET. Okay. So, how do I get my high gain? It looks like adding another n-MOSFET does not work. So, the answer to high gain is to find a device that will give us a current source. So, that no matter what the fluctuation across this device, the current is always a constant, and which means the small signal output impedance is close to infinite. So, that is the device we want. It will give you a finite voltage drop, but infinite output impedance. So, that is the magical device we are looking for. So, from our knowledge of device physics, is there a device of that kind? The answer is yes, and the device is a complementary MOS device. Okay. So, you use an n-MOS driver which is biased in saturation, and we use a PMOS load which is also biased in saturation. Okay. And this structure is supposed to be an amplifier that has got very high gain. Why is that? Okay. In the previous case, in the case of an n-MOS, when we looked at the n-MOS load, we found that the gain was being killed because of the 1 by GML term, that is the GM term of the n-MOSFET. The n-MOSFET was permitting a current through this path in response to the fluctuation in V out. Okay. So, we want a device that irrespective of the fluctuation in V out, the current will have no fluctuation or no response in current through it. We want such a device, and we are saying that the PMOS is such a device. Why is that? What is the gate to source voltage of the PMOS? The gate to source voltage of the PMOS is this, the gate to source voltage of the NMOS is this. So, it is only if either this or that nodes fluctuate will an ideal PMOS have any current through it. So, a fluctuation in V out will not cause a current through the PMOS device. Okay. So, in a case of an NMOS device, if either this node or this node were to fluctuate, you will have a current through the device. But in the case of a PMOS device, it is only when these two nodes fluctuate that you will have a current through it, and therefore, fluctuation in the output node will not cause a current, and therefore, it is going to be a device that is going to give you the resistance that you desire. So, once again, now let us analyze our final circuit, which is the amplifier with a PMOS load. So, we have a PMOS load and an NMOS driver. It could be the other way around as well. So, it is basically CMOS technology or complementary MOS technology, okay, which is basically the cornerstone of all our digital analog circuits now. So, if we look at this, we have the current through both the devices being equal, and therefore, firstly you will identify that there is no definition for the output voltage, and therefore, it becomes quite difficult to bias the circuit. But that being put aside, let us consider the small signal analysis of your new amplifier, which has got a PMOS load and a NMOS driver. So, the PMOS load has got a bias voltage, a DC bias voltage, no AC fluctuation there. So, we just ground it. So, you do not worry about that. The power supply is grounded, the ground is ground, this is V in, that is V out, that is the channel length modulation of the PMOS, that is the channel length modulation of the NMOS. And now, we see the primary difference. The current through this is the same, it is GMD V in. The current through this is V out by RDO. The current through this is V out minus V out by RLO, and the current through this is now 0, because neither is this node fluctuating nor is that node fluctuating. So, the current is now 0, and that is the fundamental difference between having an NMOS and a PMOS. And therefore, using Kirchhoff's law, this current here is equal to GM, this current in this node, that is GMD into Vn plus V out by RDO, and it turns out the gain is this, it is minus GMD into RDO parallel RLO. This is very high and that is also very high, because these are the saturation mode output resistances of the MOSFET, and this is existing only because of channel length modulation. So, if we say that there is no channel length modulation, then this becomes infinite and that becomes infinite, and the gain is theoretically infinite. So, CMOS technology can give you very high gain. Okay. So, that is why it is desirable to have CMOS technology. It can give you high gain. Okay. But does it follow the property of low output impedance? The answer is no. The high gain comes at the cost of high output impedance. Okay. And therefore, you need to have this circuit to give you high gain, and you need to have another circuit to give you low output impedance, which is not going to be covered in this in these set of lectures. But if you are interested, then you can look up any book on analog circuits, and you can look up common drain amplifiers and other amplifier topologies such as common gate, etc., etc. So, this gives you a brief understanding of amplifier design. Okay. And to summarize everything we have learned and connect everything to the device physics, what is the key message? We all know what GM is and how GM is connected. So, GM is important. Okay. High GM generally implies high gain. The next message is the channel length modulation, RO in due to channel length modulation brings down gain a little. Okay. So, channel length modulation resistance is still large, it is large, but it brings down, it contributes to lowering the gain a little, okay, small. And CMOS technology can give you very high gain, and the gain for most voltage amplifiers is a combination of the effective transconductance of the driver and the effective output impedance of the circuit. Okay. So, this is the take home message from everything that you have learned. So, CMOS, the combination of PMOS and NMOS transistors, is a very powerful tool. So, here is the summary of using the CMOS technology in an inverter configuration. So, if you are all familiar with digital circuits, you will find that this is a circuit which is called as an inverter, and from the point of view of analog amplifiers, what we are doing here is we are using the NMOS as a driver and the PMOS as a load, and also the PMOS as a driver and the NMOS as a load. So, it is a very powerful, very strong amplifier, and you will find that the output and input characteristics look like this, and you can see a region of very high gain. Any small fluctuation in the input will lead to a very large fluctuation in the output.